Hello. This session is aimed at providing insight into quantitatively understanding the potential impact of contextual driving behavior analysis that was adopted in this project on the field of actuarial and insurance premium calculation. This research has been submitted for publication in the Journal of Risk and Uncertainty. This video is composed of four main sections. I will first describe how we cleaned up our data, followed by how we created each individual variable from second-by-second trajectory data to trip level measures. For the actuarial analysis part, we take a three-phase approach by first modeling with only static underwriting data, then incorporating common UBI factors such as time of travel, hard start and hard brakes, and contextual driving data. Within each phase of the analysis, we first look at the correlations and distributions of the key variables to determine the cutoff value of each variable. Then we perform regression analysis, and from the model outputs, we calculate the relative probabilities of loss and incident rate ratios. Based on the probabilities, we then project premiums given risk factors and estimate potential premium undercharge resulting from adverse selection. We recruited frequent users of the Metropia app for this study over an 18-month period from January of 2015 to July of 2016. Our sample began with a total of 525 drivers. During the initial data screening stage, we noticed that the youngest and oldest driver groups of our users all reported 0 accidents. We decided to exclude these supposedly high-risk groups from our analysis so that our results were not affected by these extreme observations. As a result, our final sample included 503 drivers ranging from 30 to 59 years old. Collectively, these drivers completed a total of 131,537 trips, which correspond to approximately 1,090,136 miles traveled. The first phase of the analysis models auto accident rates using only static underwriting factors. We used at-fault accidents within the past 3 years, as well as accidents within the past year as our main dependent variables. We first performed the correlation analysis to define the basic relationships, and then conducted various regression models. From the model results, we calculated the relative probability and incident rate ratios that define the relationships between each variable and accident rates, and then predicted premium rates corresponding to these risk levels. Here is a sample output table that shows the relative probability and incident rate ratios. For annual vehicle mileage traveled, our findings show that people who drive more are more likely to have accidents. The base category is less than 7,500 miles. Additionally, compared to those that drive less than 7,500 miles, those with vehicle miles traveled, or VMT, between 7,500 and 10,000 are 20% more likely to have accidents, and those who drive more than 15,000 miles are more than 2 times as likely to have accidents. We also found that older people are less likely to have accidents when compared to younger drivers. Female drivers were also found to have lower accident rates than male drivers. We can further illustrate the premium effects using our model coefficients. For example, if the premium for a 38-year-old male who drove 12,000 miles per year is $1,200, then we could expect the premium for a 53-year-old to be $988. If a similar driver drives 18,000 miles, the premium would be expected to be higher. Similarly, the premium is expected to be lower if the driver drives less. During phase 2 of the analysis, we incorporate GPS data commonly used by insurers that currently offer UBI programs, such as time of travel, hard brakes, and hard starts. We tried different thresholds for defining hard brakes and hard starts. We follow the same structure by first performing correlation analysis, followed by various regression models. We report relative probability and incident rate ratios, and then illustrate the premiums. Here is a sample table that shows the relative probabilities when we include common UBI factors. We can see that a driver on the road during peak time is 1.048 times more likely to have an accident. In other words, the chance of having an accident is 4.8% higher, and both hard brakes and hard starts increase the probability of an accident as well. Using coefficients from the model results, we then project the premiums again, using different underwriting factors, and illustrate how premiums should vary based on whether one frequently travels during peak time, has hard brakes or hard starts, and other factors. For example, if we assume the actuarially fair premium for a male driver who does not tend to travel during peak time and does not have qualified hard brakes or hard starts to be $1,200, then we can expect the premium for those that frequently have hard brakes to be $1,420. Those that tend to have hard brakes as well as hard starts and also travel during peak time have the highest premium at $1,651, as the probability of loss is the highest for this group. The prediction for female drivers follow the same pattern, and the premium from female drivers are expected to be lower than that of the male drivers with similar driving characteristics. Next, we compare the amount of premiums an insurer should have charged and would have undercharged if they were to miss out on any important underwriting factor. For example, if an insurer were to exclude hard brakes in its underwriting, it could potentially undercharge a male driver by $140. If the insurer excludes both hard brakes and hard starts, it could undercharge a male driver by $214. In the third phase of analysis, we further incorporate contextual driving data. There are two main factors considered here: speeding and relative speed. For the speeding factor, we consider not only the driving speed, but also the speed limit as well as congestion level. For relative speed, we consider not only the direction of relative speed, but also the roadway prevailing average speed. We use different thresholds for defining speeding and relative speed variables to allow for variations in risk buckets. We adopt the same structure as the previous two phases so readers can easily follow the flow of the analysis. Here is a sample output table for speeding analysis. For the speeding factor, we consider not only the extent of the driving speed over the speed limit, but also congestion level as well as the speed limit of the section of the road. The main findings from speeding analysis is that speeding could result in higher accident rates regardless of congestion or not. However, the increased chance of having an accident from speeding is greater when there is an open traffic flow, and this is especially true when the speed limit is 60 miles per hour or above. From the model outputs, we once again estimate the relative insurance premium rates corresponding to whether a driver tends to be speeding or not, whether the driver is speeding during congestion, and the speed limit when speeding takes place. For example, if we assume the actuarially fair premium for a male driver that does not tend to drive significantly faster than the speed limit is $1,200, depending on whether a driver tends to drive faster than the speed limit in different situations, the actuarially fair premium for a male driver ranges from $1,200 to $2,348. For a female driver with the same characteristics, premiums range from $780 to $1,572. For both genders, premium is lowest when the driver never or seldom drives faster than the speed limit, and the premium is highest when a driver tends to be speeding under all circumstances. We also further perform premium projection and calculate how much an insurer could possibly undercharge if it does not consider speeding information when pricing auto insurance. For example, we found that an insurer that does not include speeding information in underwriting could charge $1,482 for a male driver, but the pricing would have been too low and they should have charged $1,964. In other words, the insurer would have undercharged a male driver $482. The same can be calculated for a female driver. We also perform a similar analysis on relative speed, and here's a sample output table. Consistent with what we reported before, our findings suggest that the probability of having an accident would increase when one drives faster than the link speed or slower than the link speed when the link speed is at least 40 miles per hour. However, when the link speed is below 40 miles per hour, driving slower than the link speed is not associated with a higher accident rate. Based on the results, we then estimate the probability of loss and project actuarially fair premiums for both male and female drivers. For example, if we assume the actuarially free premium for a male driver who does not tend to drive significantly faster than the link speed is $1,200, then the projected premium for a male driver would range from $1,091 to $3,391. For a female driver with the same characteristics, premiums range from $690 to $2,256. Premiums are lower when a driver does not deviate from link speed, with the exception of driving slower than the link speed when it is slower than 40 miles per hour. Premiums are the highest when a driver tends to drive much faster as slower than the link speed, but does not slow down when that link speed is slower than 40 miles per hour. Our findings suggest that driving much faster than the link speed can contribute to higher premiums regardless of what that link speed is. Driving much slower than the link speed when the link speed is greater than 40 miles per hour could also contribute to an increase in premium. However, people who drive at a speed that is slower than the link speed when it is less than 40 miles per hour can expect to pay a lower premium. Afterwards, we calculate the potential undercharged premium amount when the relative speed is not considered. As can be seen in this table, the undercharged premium for male drivers is $726 on average, or 27.6%, while for the female drivers, the undercharged amount is $543 and 31%. In conclusion, through numerical analysis, we were able to prove that driving behavior is context-sensitive, particularly with regards to traffic conditions. Our results show that vehicle mileage traveled, pedal operation, Speeding behavior and driving speed relative to other vehicles on the same road are all significantly related to accident rates. The findings of our study reveal the benefits of incorporating insurance telematics data in the setting of auto insurance premium rates. According to our analysis, insurers that omit individualized driving factors could significantly undercharge their policyholders and suffer underwriting losses due to adverse selection. Thank you, and should you have any questions or comments about our research, please don't hesitate to contact us via the information on the slide.